All right, in this lecture, which is going to be a very brief lecture because I think most people have already encountered basic trig functions and complex numbers. But in this lecture, that's pretty much what we're going to cover, and what we want to do a little bit differently is to draw the relationship between trigonometric functions and the complex numbers and complex plane. So be a couple of just kind of different things that we'll look at here in this math review. Here are some references for if they're of interest and if you need further investigation, particularly of the trig functions and trig identities. This is a kind of a pre-calculus concept, but as we go through this lecture, I want to point some things out that particularly in engineering we do in reference a little bit uniquely. So as you know, in trig there are relationships within a right triangle. A right triangle meaning one of the angles is 90 degrees. The two sides that are adjacent to the 90-degree angle are known as the sides, and the third side that's opposite the right angle is known as the hypotenuse. So the most common of these relationships are sine, cosine, and tangent, and in fact we rarely use anything other than sine, cosine, and tangent. And because there are distinct relationships between sine and cosine that vary by a 90-degree shift in phase, then oftentimes in electrical engineering you will find, particularly when we're discussing things like AC voltage and current, we will only use the cosine function. So because these are all interrelated to each other and one can be expressed as another, standards have sort of evolved over which ones are the ones that are most widely used. But all of them are widely used in engineering and physics, and different ones take different priority depending on what part of engineering you're in. So initially we'll define the trig functions with respect to the right triangle and relationships in space. So here's a picture of the right triangle. You can see the various sides are labeled, the opposite, the adjacent, and the hypotenuse. And then basically the trig functions just consist of ratios between the three sides. So here's the figure repeated again, and then here is expressions, and we're referencing here only angle A, just so that you can get a definition or a reminder of the definition of the six trig functions. Here they all are, and you can see, I'll let you just explore on your own if you've forgotten any of those. And as I said, really we'll see cosine, sine, and tangent mostly in this class and in the classes that you'll encounter. Now, if you took a class in probably either Algebra 2, maybe Geometry, and maybe some of you even had a trig class, or maybe your trig class was folded into your pre-calculus. But if you took a class like that, either in high school or in early college, you probably came across what is known as trig identities. These are just statements that show equivalency between one form and another. This first one is particularly useful. Some of these, especially these first three, are useful as well. And then it's also useful to know that the sine and cosine values repeat at integer multiples of 2 pi. So k here is an integer. Now in physics, the use of trig functions is very common to describe motion and forces, as well as in civil and mechanical engineering. The main use is because we can then take these problems and resolve them into individual dimensions, which makes them easier to work because we're only working with one dimension at a time. And so typically you're working with this notion of spatial trigonometric functions. In electrical engineering, trig functions are used to describe sinusoidal oscillations in time, the kind that we see present in an AC voltage or in electromagnetic fields. And these are referred to, or electromagnetic radiation. And these are often referred to as sinusoids or sinusoidal functions. Mechanical engineers use sinusoidal functions in time as well. These tend to represent vibrations and mechanical waves. So that brings into play then the concept of the unit circle. So here's a xy set of axes, and here's the origin, and here is my triangle. So here's my point A, Here's my 90-degree angle. Here's theta. And so we always define typically the angle theta as being the angle that we make with the horizontal axis on the unit circle. And the horizontal axis is typically starting at the positive x-axis. And so as we go around the unit circle, theta is going to go from 0 to 2 pi, and then we see we're going to start over again, and then we're going to trace out 0 to 2 pi again. So if a parameter is changing sinusoidally, then if we were to track only x, we can see that as theta goes from 0 to 2 pi, x will go from plus 1 over to minus 1 and then back to plus 1. So x is just going to, the length of x is just going to oscillate along this axis, and the length of y is going to oscillate along the vertical axis. And in fact, we could pick any direction and we would see that same oscillation. So this gives you an idea of how if we allow, if for example our angle is proportional to some omega t, where omega is a radian frequency of rotation and t is a time, then we would expect to see theta vary in time. In this figure we see some common angles. I don't have all of these memorized. The ones that we always memorized were obviously 0 degrees, the 30, 60, 90 right triangle, and the 45-degree triangle. And so, you know, there's nothing in this class with regard to this kind of thing that you have to commit to memory, but certainly it's useful as we talk about things in other classes to know, for example, that the tangent of 45 degrees is equal to 1. And some of this is intuitive, and if it's not intuitive, then you can either look at the unit circle, or you can plug the degree into your calculator, or convert that to radians, which is conveniently shown above here for you. But this is a nice table, and indeed a lot of problems worked in classes and given on tests in various engineering classes. People will choose the 30, 45, or 60 just so that the numbers are easier to work with. So the last thing to look at with regard to the trig functions are the derivatives and integrals. So here's a table that presents the 6 trig functions, and then the second column shows their derivative, and the third column shows their integral. All right, so a sine wave or a sinusoid is a mathematical curve. It describes a smooth periodic oscillation. A sine wave is continuous. It occurs in both pure and applied mathematics, as well as physics, engineering, signal processing, and many other fields. And its most basic form is a function of time. It's given below. So y of t is our function, and then that's equal to a times the sine of 2 pi ft plus phi, or the sine of omega t plus phi. So a, the amplitude, is basically the peak deviation of the function from 0. F is the ordinary frequency, the number of cycles that occur every second. Omega is the angular frequency, and so that is, if you realize that there are 2 pi rotations per cycle, you can multiply f by 2 pi and you'll get radians per second. Phi is the phase in radians when its cycle of oscillation is at t equals 0. Now I do want to make one comment that's made up here, and that is that in electrical engineering and in signals, it is not uncommon, especially in power engineering where you're talking about AC voltage signals, it is not uncommon to see this phase angle specified in degrees. And so if that's the case, they'll write, plus 30 degrees. You'll then have to convert that to radians if you actually want to plug in a time and get a number so that omega t and phi have the same angle unit. So here's an example of a sine and cosine function. You can see that there is a phase shift or a phase difference between sine and cosine of 90 degrees. So in biomedical signals and measuring, the sinusoidal function is always expressed as a cosine function, almost always. So a typical AC voltage is expressed as some V sub 0 cosine of omega t plus phi, The cosine function is used because later on we'll see that these sinusoidal functions are very closely related to exponential functions. All right, and once again, here are some extended derivative and integral formulas. All arcsine means is the angle whose sine is. So it's an inverse operation. So if we're given 1/2, then we would figure out what angle has a sine of 1/2. All right, the next thing to discuss in this lecture is complex numbers, and I'm discussing them here firstly because I don't really feel they merit their own full lecture, because everyone taking this course should have seen these in the past, and secondly because there are some relationships between certain forms of complex numbers and the trigonometric functions. So first of all, a complex number consists of a real part and an imaginary part. And the convention is to write this as the sum of these two parts. So we have C is equal to A plus JB, where J is the square root of -1, or J squared is -1. We're writing it in this class as J and not I, the imaginary, because electrical engineers use I to represent current. And so because we don't want a conflict in notation, electrical engineers just by convention have typically defined the imaginary as J. Now this can also be written in what we refer to as polar form, where we have the same C that's equal to the absolute value, which is also known as the magnitude of C, times e to the j phi, which is known as the phase of phi. And you can convert back and forth between these two forms. And a lot of times students will try to memorize the formulas that give you the conversion back and forth, but I just want to show you the figure where all of this is defined. So here is what we refer to as the complex plane. The vertical axis is the imaginary axis. The horizontal axis is the real axis. Positive is from left to right and from bottom to top. So if we have a complex number, a plus jb, that plots here, but it is not actually a point, it is actually a line that looks a lot like a vector, if you remember anything from vectors and from physics. So it looks a lot like a line, it has a direction, and it has a magnitude. So if we just write a plus jb, we can plot that on a complex plane by finding the real part, which is a, and the imaginary part, which is b, putting a point here with those two coordinates, and then drawing a line that goes from the origin to that point. So this is actually my complex number, is this line, and this is what we sometimes can refer to as a phasor. Now the absolute value of C is going to be the length of the line, and so you can see then that the absolute value or magnitude of a complex number can be related to A and B through the Pythagorean theorem. The angle here, as you can see, is the inverse tangent of B over A. So these are the relationships. If you have your complex number in rectangular form and you wish to convert to polar form, these are the conversion formulas. You can then get A and B back by using trigonometry and saying that A is C times the cosine of phi and B is C times the sine of phi. So those are the primarily relevant formulas for complex numbers. I will talk about one other notation that you see in electrical engineering, and that is what we refer to as phasor notation. So in phasor notation, sometimes this E and this J are omitted, and we write that as angle phi. And usually in this notation, these absolute value signs or magnitude signs are omitted. So you will just have C angle phi, where C is the magnitude or amplitude and phi is the phase. So that's fairly common in electrical engineering in a lot of classes to see things denoted that way. All right, I'm pretty much at the end of this review lecture. I do want to mention one thing about complex numbers. Complex numbers, like ordinary numbers, can be added, subtracted, divided, and multiplied. The easiest way to do addition and subtraction is to leave your complex number in rectangular form. Multiplication and division are much easier to do in polar form or phasor form. And so if you need additional resources on how to do complex number math, please let me know and I can provide those for you.